Okay, so how is everyone today? Good. So what did we cover last time?
Continuity.
We had just gotten to continuity. We just gotten to continuity, and I had raised a question. So today is the 21st? Yeah, first. So I had raised a question that the function f of x equal to 1 over x, which of course everyone knows what it looks like, the reciprocal function. And then the question that I raised was, is this a continuous function? And what's the answer to the question? Yes. Yes, this is a continuous function. So, is f continuous? Yes, it is. Now you might object and say, I don't know, it doesn't look like I'd be able to draw across 0. If I were to attempt to draw this function, I couldn't do it to get from the bottom part to the next part. But you have a look at the definition of continuity. What is in the very first line? In particular, it's continuity at a point. What must be true about this point in question? It has to be in the domain. Okay, so the question, is this function continuous at 0? The question itself is wrong. To ask whether or not this function is continuous at 0 is to misunderstand what it means to be continuous. It's to misunderstand. So, is this function continuous? Yes. It's not connected. It consists of two pieces which are disconnected, but it's still continuous. Similarly, we haven't gotten to it yet, but in the same kind of vein, I could ask, well, what about the absolute value function where we delete the pointy spot? We just delete that one. Is that function continuous? Yes. Yeah, because the point where you're concerned about is not even in the domain, so it doesn't even make sense to ask whether or not it's continuous at 0. Is this a continuous function? Yes, it is. Is it a differentiable function?
Yes, but not at that point.
Yeah, well, that's like saying that. That's like saying that. Here's a nice statement. All horses have hair. But then you might object, but this doesn't have hair. But what's wrong with my objection? It's not a horse. Right? Well, or pocket protectors, right?
Explain that.
Did you have a question?
So as far as continuity, then we have to define a domain. So
well,
in this case, with this graph here, the domain is defined as all real values other than 0.
Yeah. Because I said out loud that this is the definition of the function, that f of x is absolute value of x except 0 is deleted. So it's absolute value of x when x is not 0, and then it has no other definition.
So then in the case of the 1 over x, then we say it is continuous, assuming our domain is defined to not include 0.
Right, because well, it must, right? 0 could never be part of the domain of this function.
It's undefined at 0, so
Right. So what's at play, I think, that may be confusing is that when a function is defined by an expression, expressions have a natural domain. And what is the natural domain of an expression? It's the largest possible set on which the expression could be defined. So what is the largest possible set on which this expression could be defined? Anything but 0. So when a function is defined by an expression and its domain is not explicitly stated, then it is understood that the domain is the natural domain of the expression defining it. So, did I explicitly state the domain of this function? I did not. But this is a function defined by an expression. The natural domain of this expression is anything but 0. So that's the domain of this function. That's the implied understanding. Other questions? Okay.
One quick question.
Yes?
You said that the second absolute value, that one is differentiable.
It is.
Okay, just making sure.
It's differentiable because, you might complain, well, if that point were there, it wouldn't be differentiable there. But it's not there, right? So if you happen to be on the downward side, then if you're a little bitty creature, everything looks downward. Everything looks slope -1 to you, if you happen to be over here. If you happen to be on the other side, everything looks slope 1 to you. And you can't walk to the other side. You can't get over there because that point's missing. Yes?
Why did you take out the point for it to be continuous?
Well, I didn't. Absolute value is continuous.
Just making sure.
Of course, absolute value is continuous, but it's not differentiable.
Okay, I was just making sure then.
Yes?
So before when we call those things discontinuities, that in those cases the domain was the real.
Well, I wasn't there in your calculus class, but I would say this is that this function, to say it is discontinuous at 0 is to misunderstand what it means to be continuous. It's a misunderstanding. So it's a point that your previous calculus instructor glossed over, I suspect. Okay. Now, if I was to edit this definition and say f of x is 1 over x when x isn't 0, and then something else when it is, and put a point here, like just fill in a point right there, then that function would no longer be continuous. If I was to just select some point. Yes?
Wait, so if the function was defined as x is all real numbers, would it not be continuous then?
It can't possibly be defined in that way. Because to say, if you were to say that the domain of this function is all reals, then tell me, what would you do if I handed you x is 0? You couldn't do anything. You would, the universe would explode. Yes?
So can we say for a function to be discontinuous, the point in question must be defined?
Must be defined. Yeah, it simply must be defined. Otherwise, you're mistaking the definition. It would be like me saying, please go to the store and bring back a red apple. And then you bring back this. And then I object. And you say, it's clearly red.
Are we wrong?
Yes, because it wasn't first an apple, right? It would have been better if you brought back a green apple, because at least it would have been an apple. Yes?
Okay, so you just mentioned the limit of x tends to x naught.
Yes?
But then in, let's say, a piecewise function where in our previous class we defined this to be discontinuous at the point, which I know is technically not my definition, but
Well-
the limit from the left is not the same as the limit from the right. So when we say that the limit of x tends to x naught is equal to the function at x naught,
Yes.
does that mean that the limits from both sides must also agree? Or is that implicit? Is that implied in that statement?
To be continuous?
Yeah.
Yes. That's part of it. But in the first place, before any of that, it has to be a point. So you might be objecting and saying, well, the limit here appears to not exist and not exist from the left and right. No objection. But the fact that you're even considering that, even though there's not a point there, that's the problem.
Like, so in the event that the piecewise function would be defined on the point, the limit would not agree from the left and the right at the break of that piecewise.
We'll need a homework exercise to get this all sorted out. Okay, we've got to continue. Okay. So here's something nice. So the square root of 2, if we were to plug this into our calculator, then it would start to, the calculator would respond with something like this. 1.414, 21, blah, 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 blah. So it would respond in such a way, and it would only give us finitely many digits because that's the best a calculator can do. But the square root of 2 is irrational, so it never has a repeating pattern. So it just keeps going forever. So I want you to consider the following sequence. A sequence where the 0th term is 1, the first term is 1.4, the second term is 1.41, the third term is 1.414, etc. So that what xk is, notice that x1 agrees with the square root of 2 up to 1 decimal place, x2 up to 2 decimal places, x3 up to 3 decimal places. So xk agrees with the decimal digits, with the digits of square root of 2 out to digit k. Okay. So this is a sequence. Is it going to converge?
Yes?
One of those answers is right. So will it converge? It will. So what is the candidate to check whether or not it will converge? What do you suspect it would converge to? Square root of 2. If it's going to converge to anything, it seems like it must converge to the square root of 2. Well, let's show that. Let's show that xn converges to the square root of 2 as n goes to infinity. Well, let's consider. What's the difference between xk and the square root of 2? So that is to say, what would happen if you subtracted them? In the first place, the units place would be 0, right? Because this one, we always have a 1, and then we'd subtract the unit away. And then how many digits past the decimal would be zeroed? There'd be k of them, right? So it would be 0.000, and there'd be k of those. There'd be k zeros, and then, yes?
I was going to say, should we put a negative in front? Because number 2 will always be bigger than
Well, it's an absolute value. But I agree. I agree that square root of 2 is the larger of the two. So this would be digit k plus 1, and then digit k plus 2, etc. So that's standing in for some number 0 through 9, the next digit 0 through 9, ... Okay. So now, this pardon me, this is less or equal to even, I'll say, less than a power of 10. Right? So what's the biggest this number could be when all of the remaining ones are 9, I guess. But that doesn't happen because at any rate that can't happen because then square root of 2 would be rational. But even supposing that they're all 9, then that would mean that if this were a 1 and then the rest zeros, that number would be bigger. So this is less than what power of 10? 10 to negative k. That's just to say that this is less than 0 point, bunch of zeros and then a 1. It's less than that. So what we're saying is that because you can make this arbitrarily small, because 10 to k can be as small as you want, that means that we can get xk as close to square root of 2 as we want. So can we get it this close? Yes, we can get it this close. Can we get it within the width of a hydrogen atom? Sure, we can get it that close. No problem. Whatever distance you like, we can get it that close. So, we can get it as close as we want. Any question about this? Okay. So, next. We need some... Is it time for this? Yeah, time for this. Okay. So this is a proposition. So there's two parts to the proposition. So we're going to state and then prove and then state and then prove. So in the first place, let xi be a sequence on a set that is closed subset of Rn. And by the way, what does closed mean?
It is a complement of an
The complement of an open set. That's what it means to us. So it's going to mean something else when we're done with, it's going to mean something else also when we're done with this. But right now, closed means the complement of an open set. Okay, so then let xi be a sequence on a closed set. And suppose that xi converges to point A. And this point A is in Rn. Rn. So the claim is, the proposition is, that A has to be in X. So X is a subset of Rn, and we've got a sequence in X that converges to a point in Rn. The conclusion is that this A must in fact be in X. Okay, so that is to say, if we have set X, and then we've got a bunch of Xi's that are doing their thing inside of X, wandering around being in a sequence. So that is like, this is the X1, X2, X3, etc. Then we've got some point A. We've got some point A. It must be the case that A is maybe fully inside. A could be totally inside of X. A could be here. That would be okay. So these two scenarios would be okay. Inside or on the boundary. But what we want to show is that it couldn't possibly be the case. It couldn't possibly be the case that point A is way outside. Okay, so this one is not okay. Well, let's prove it. Let's prove that it's impossible for A to be way outside in the following sense. So suppose the contrary. I didn't write the conclusion. Then what we're supposed to show is that A is in X. So suppose the contrary, that is to say that A is outside of X. That A is in Rn minus X. Well, notably, by hypothesis, X is closed. So how about this set, Rn minus X? It's open. So that means that this is open. And then what does it mean for A to be in an open set? What can we do to A inside of that open set? Yeah, we can draw a ball around it. We can draw a ball around it. So let's draw such a ball, such that this is true. Therefore, there exists a radius positive such that the ball of radius r centered at A is contained in Rn minus x. So in particular, because it's contained in the complement of x, this ball is entirely outside of x. This ball doesn't play with x. So here we've done it. So there's point A, and there's radius r. Okay. So now, what's going to go wrong here? Because remember, we're doing this by contradiction, by supposing the contrary. What will go wrong here? The claim is that the red points, the little red dots, they're a sequence of dots that I put in there, and I should be able to get those dots as close to A as I want. Yes?
There should be an infinite amount of dots within the ball. There's gonna be none.
Exactly, right? How many of the red dots need to be in this ball? Infinitely many of them. That's what it means to have a limit. And how many of them are in there? less than infinite, right? Exactly 0. Okay, so can you see it? What this ball does is it separates A from the set. Therefore, A cannot be the limit. Okay, very good. Any question about that one? So now, this was an implication. The implication is that if you have a sequence on a closed set that converges, then that point that it converges to must be in the set. Furthermore, what if we turn the hypotheses around? What if we turn the propositions around, that is to say that suppose that X is a subset of Rn such that every sequence on X converges. And in particular, it converges to a point in X. So notably, in proposition 2, do we know if X is open or closed? No, we don't. We just know X to be a set. X is a set. And it has the property that every sequence on X converges to a point in X. Then what will be true about X? Then X is closed. Okay. So we want to show that, yes?
This might be a really weird case, but if we add an x and it has its points, but in the middle there is one point missing, which we said is A. So A is not within x, but any epsilon drawn around A will be.
This is fine. That's fine, but such a set couldn't possibly be closed. Such a set couldn't possibly be. Sorry, I lost the train of thought.
You could have a sequence that converges to that point, which is not inside of the set. And so,
But then such a set doesn't satisfy the hypothesis.
Yes.
Yeah. So by hypothesis, we're talking about a set such that every convergent sequence converges to a point that is in the set. So what you supplied, the punctured disk, doesn't satisfy the hypothesis. Okay, so we want to show that X is closed, but we don't have a good handle on what that means, because at this point, when you're trying to get things defined propositions all over the place. You can't really show that something is closed. Rather, what is it that you do?
Its complement is open.
You show that its complement is open. Okay, so what we want to conclude is that X is closed. But what we're going to do is we're going to show that X's complement is open. Okay, so we have set X here. So this is set X. And to show that something is open, that means you can take an arbitrary thing in that set and put a ball around it and you never leave. That's what it means. So we'll say let A be in the complement. So now, don't be misled by the way I drew this. Just because I drew a solid bit, that doesn't mean that this set is closed, right? That's what we must show. So I think it's clear that if I select a point way far away, we could surely put a ball around that one. Okay, that would be sort of a boring point. It would be a boring point. So what we really need is points that are right here. So even up to the boundary of X. Now, if I'm talking about a point that's on the boundary of X, does that mean it's an X? So can someone give me an example of a set X and a point that's on the boundary but's not in that set? Yeah. The open unit interval. One is on the boundary, but not in the set. Okay, so how will we do this? What do you think? Okay, so we'll say let A be in there. We need to show that there exists an epsilon positive such that the ball of radius epsilon centered at our point A is a subset of the complement. That's what we need to show. If we could produce such an epsilon, then we would be finished. But again, we're going to do it by contradiction. We're going to say, well, let's assume that it's just impossible to do it. So let's assume no such epsilon exists. What that's saying is that no matter how small of a ball, that you select, you're always going to pick up a point in X. There's always going to be at least one. You can't isolate it. So that means that we could let epsilon be 1 over n as a sequence of epsilons, right? So that we can make it smaller and smaller. Then that means that the ball of radius 1 over n centered at A contains a point in X for all n. Okay, now what? Okay, well, so for all in, so then let's say that from here we let x in be any point that's in. this. Well, it's in this. So that is to say, it's in the ball and it's in X. It's in the ball and it's in X. Then what is that saying? That means that xn gets arbitrarily close to what point? It gets arbitrarily close to A. Then xn must converge to A. I guess these need hats. So this xn needs a hat. But this is a real problem because this sequence, where is the xn sequence sitting inside? It's sitting inside of X. It's sitting inside of set X. And it converges to A. And therefore, by hypothesis, where is A? It's in X. But we just got finished saying that it wasn't in X. So we've arrived at a contradiction. A has to be both in X and not in X. So where did we make the contrary assumption? That you couldn't find such an epsilon. So that means that actually you must be able to find such an epsilon and the complement is open and the set itself is closed. Good. So what this means, the name of this, the sort of intuitive name of this proposition is that closed sets are closed under limits. That is to say, you can compute limits inside of this set, and you'll never leave. You won't ever find yourself jumping out of it. Whereas in the open unit interval, you could find a sequence of points which converge to a point outside. So for example, 1 over n is in the open unit interval for every n. But what does 1 over n converge to? 0, which is outside. Okay. Good. Any question about that one? Yes?
So, if we have a set that does not include the boundary, so an open set, and then we put our A on the boundary, we still have every sequence in that set converging to a point on the boundary.
No, it's that every sequence which converges. So you've got a sequence, all of the elements are in X, and this sequence converges in Rn, in the bigger space. The hypothesis is that, in fact, the convergent point must be in X. So the example you gave me, an open set, and selecting a point on the boundary doesn't satisfy the hypotheses.
Which aspect of the hypothesis did it not satisfy?
Suppose that we have a set X and a sequence on X, and such that every sequence on X converges to a point in X. Yeah, converges to a point in X. So, if you might be imagining the open unit disk or something, and going to the boundary, well, that doesn't satisfy this hypothesis. Yes?
I understood where we assume the inverse, where no such epsilon, and then can you explain the next part? Where you let epsilon. So you're drawing a ball around the green dot, and you're saying that.
So, in picture, what it's saying, what the contrary assumption is saying is that every ball intersects X. So what it's saying that every ball looks like this. For every 1 over n centered at A, then you've got point A, and you've got a ball of radius epsilon, and no matter how small you make that ball, you're still picking up parts of X. So this is set X. And no matter how small you make epsilon. You're always going to get points in x. So what I'm saying is, because you always get a point in x, let this one be xn. And then I'm making the balls smaller and smaller and smaller and smaller, and I'm marching these red points straight to A. So I'm constructing a sequence going to A one term at a time. Yes? Okay. Yeah, this is the first time y'all are seeing a lot of these things, so they're a little complicated to deal with, to get a handle on them. But don't worry, it's going to get worse before it gets better.
So we're saying that A is simultaneously in and outside of X, because for
Well,
the reals minus, it's for contradiction.
no, it's for contradiction. What we want to show is that it's open. So we're saying, suppose that we have a point that's in the complement, and we would like for this to be open. So as a result of concluding that it's in the complement, and as a result of concluding that no such epsilon can produce this, it must not be in the complement. So we have two contradictory things. So we have to give up something. We can either give up that it was in the complement, but then there'd be nothing. Then the whole argument would be ridiculous. You have to assume this. This is the one you must give up, that there's no epsilon. We'll keep going. There'll be more of these. These kind of proofs right now, you can think of them as preparing you for your upper level classes. So you need to get used to seeing these arguments. Okay, next. So I want you to imagine the half open, which is a term that we haven't defined, but you know what it is. The half opened unit interval, 0 to 1, including 0, but not including 1. Furthermore, I want you to consider points and their representation is going to be in binary. So we're going to have binary points. So if this was in decimal, the usual thing, then all of the numbers that are in here, their representation, their decimal representation would start out with 0 point something or other. They'd all have to be that way. Okay, because we're not including that one, so it's out. And you couldn't have 0 point all nines because that's that one. Okay. Also in binary, all of these must all start out with 0 point something or other. So all of these look like, in binary, 0 point x, 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 x. So all of them look like this. Okay, even better, let me write it like this. 0 point, the first bit, the second bit, the third bit, etc. So now, we're going to split this interval evenly, so that the split goes like this. So Gesundheit, we'll split this one and this one. So to the left, we're going to take 0 to half, and to the right, we're going to take half to 1. Notice that we're always going to have the left endpoint, but not the right endpoint. So now, doing this split, what this split does numerically, it's telling you, if you go to the left, it's telling you what B1 is, what the first bit is. What's the first bit if you go this way? It's 0. This is saying that B1 is 0. So that means that all of the numbers in here, their decimal representation, binary representation, starts out with 0.0 and then B1, B2, etc. Whereas if you go to the right, what is that telling you about the first bit?
1.
That the first bit is 1. So that all of the numbers in this interval will look like 0.1 and then the second bit, the third bit, etc. Did I make a mistake?
Yeah, B1 on the left side, yeah.
This should be, yeah, thank you. This should be 2 and this one 3.
No, that's not a mistake.
Oh, did I make another one? It's
Yeah,
totally possible.
well, 1/2 is 5.
In binary.
Oh, binary.
In binary. So in binary, 1/2 is 0.1.
Okay, so you did in binary then.
Okay, good. Yeah, these are bits, not digits. Okay, so now let's split each one of these again. So now we'll have 4 intervals. So the leftmost one would be 0 to 1/4. Then we would get 1/4 to 1/2. Here we'd have 1/2 to 3/4, and then we'd have 3/4 to 1. Okay. So now, if you think of this like making a decision, you're here and you decide to go left or right. From here, the decision tells you the first bit. What does this decision tell you? The second bit, right? So if you travel this way, then that tells you that B2 is what? 0. And if you travel this way, then what's B2? It's 1. So this would be B2 is 0, and this one, B2 is 1. Okay, so that is to say that all of the numbers, in binary, their representation in this interval is of the format 0.00 and then B3, etc. This one is 0.01 and then B3, etc. This one is 0.10 and then B3, etc. And this one is 0.11 and then B3, etc. So I think, yes?
So what binary is telling us is which half of the last division is on.
That's right. That's all that it's saying. So I think from here, you could probably tell me, suppose you were here and you chose to go right. So you were here and then you chose to go right. Then what would the first 3 digits of your binary representation be? 0.101. That's where you'd be. So every single binary number can be construed as traversing this tree down the line. Okay, very good. So this is the line. So now we need to even more quickly do what would happen if we did it on the plane. So now, whoops. So by this I mean the half closed, half open unit square. So this is the point 0, 0, and this is the point 1, 1. Okay, and we're not including the upper boundary, but yes, we are including the lower boundary. Okay, so now, as a result, all of the numbers in here have in the first place 2 coordinates, and they are of the form 0. Any bit, right? Because we haven't made any choices. So B1, B2, etc., and we'll call these ones C1, C2, etc. So now we're going to bisect, but we're going to bisect in both directions. So how many pieces will we have? We'll have 4 pieces. So we're going to take this and cut it halfway that way, and we'll have the following. Okay? So that is to say, now there's not, for each direction there's a choice, or if you like, there's 4 choices. Okay, so this one, the lower coordinate of this one is 0, 0. The lower coordinate of this one is what? 0 and then half. This one would be half, 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 half. And this one would be half, 0. Okay. So now, suppose you find yourself in here. Then what is the first digit of each binary representation if you find yourself in here?
0.
So because you went left, the x coordinate starts with 0. And because you went up, instead of going down, you went up, this one is what? 1. So this is 1. And then B2, and then C2, etc., etc. How about, what are these going to be? This is 0 and 0, right? So this would be 0.0 and 0.0, and then B2, etc., C2, etc. How about this one? You went right and down, so this would be, because you went right, it'd be 0.1, and then B2, etc., and because you went down, it would be 0.0, C2, etc. So this is the same thing as the previous page, except we have to make 2 choices. Okay. Then finally, this one would be 0.1 and also 0.1, B1, C1, etc. Yeah, 2. Okay, good. Then I think you can imagine that, okay, now we could take one of these and split it into 4 and then draw 4 more, but I think you get it now. So every time you split, that's equivalent to making a choice about the binary digit, the bit. Okay, good. So now I'll let that stew in your head for a few minutes. Here's the definition of a bounded set. A set X, which is a subset of Rn, is called bounded when there exists a radius which is positive such that X is contained in the ball of that radius centered at 0. So that's a math definition, but can someone tell us what this means? Yes?
Doesn't go to infinity in any direction.
Right. So it's sort of like conceptually, you're saying, okay, we've got I'm going to draw the plane, but understand that this is an Rn. So we've got a set X, and maybe it's even a disconnected set, so that we've got a point there, and then we've got all of this right here. That's all in there, and then we've got some other stuff too over there. This is all, that's all in set X. So what is this thing? That's a ball centered where? Centered at the origin. So the question is can you draw a ball big enough centered at the origin so that you could enclose all of it? Yeah, that's true for this one. So this is the ball of radius r. So that red stuff is bounded. But the x-axis is not bounded. You couldn't draw a circle around the x-axis. Okay, yes?
Just based on the definition, why can't we consider infinity greater than 0?
I'm sorry?
Because we could put r equals infinity and it'd still be greater than 0. And
Well-
it's an infinite ball.
Well, so that would be set, then there would be nothing to say because every set would be definitionally bounded because it would be sitting inside of the whole shebang.
So we're with the assumption R cannot equal that.
Yeah, R's are real.
R's are real, okay.
R's are real. Okay, so now, closed sets are closed under limits, or, and also you need to remember that closed sets are the complement of open sets. Then now we know what a bounded set is. So sets that happen to be both of these are the happiest sets that mathematicians can have. Okay, so what's the name for sets which are both closed and bounded? Compact. A set which is closed and bounded, we need here's an important proviso, a non-empty set. Set which is closed and bounded is called compact. So, how about this one? Is it compact? It's bounded, but it's not closed. It's not closed because you could tell me a point which is on the boundary that's not in the set. What point is on the boundary but not in the set? 1. So this is not compact. How about this one? Yeah. So this one is bounded but not closed. How about something that's closed but not bounded? Is this compact? No. Okay. So closed and bounded.
But doesn't the first one have an open complement though?
No, because R, let's compute it right now. R minus this would be equal to what? We'd have negative infinity to 0, and that part would be open. And then union what? 1 to infinity. So because of that point right there, yeah, because of that point right there. Okay, good. So now, maybe on this page. Nope, not enough room. So just to introduce a little bit of language, suppose that we have the following sequence. I goes to, say, I squared when I is even, and it goes to 1 over I when I is odd. So this is a sequence, but it in a sense has kind of two minds. When it has even inputs, it does one thing, and when it has odd inputs, it does another thing. So let's list out a few of the terms. And I'll say that this is going to be for I positive. Okay, so the first term then would be an odd term, and it would be 1, because 1 over 1 is 1. And then 2 squared is 4. And then 1 over 3. And then 3, and then 4, that'd be 16 would be the next one. And then 1 over 5, and then 36, etc. Okay, so this is a sequence. This is a sequence. Does it converge? No, it doesn't converge. It doesn't converge because, in a sense, you might say, the even terms are misbehaved. They're getting really big. Whereas the odd terms are kind of well-behaved. Are the odd terms going to converge? The odd terms will converge, and where will they converge to? 0. So, when you take a sequence and you select just parts of it, this is called a subsequence. So this has a convergent subsequence. It also has a subsequence which is not convergent, if you take the even ones. The even ones are a subsequence, but they don't converge. Okay, so now here's one of the theorems that holds all of calculus together. Let X, subset of Rn, be compact. And let Xi be a sequence on X. Okay, so we already know that if Xi happens to converge, we haven't assumed that. If Xi converges, then we know that it converges in X. Why do we know that? Right, because X is by hypothesis compact, which means it's closed. So if this converges, it converges in X. Okay? Let X be a compact set and let Xi be a sequence on X. Then there exists a convergent subsequence of X. Okay, I'm notably not saying two things. In the first place, I'm not saying that this converges. Furthermore, I'm not telling you exactly what it converges to. But I am telling you that somehow we can choose a subsequence, and that subsequence is going to converge, and furthermore, it's going to converge in X. Okay, so then, what's the name of this? Those of you who've taken T-Calc. Not quite. But it will be a little bit related to that. That one. This is the Bolzano-Weierstrass theorem. Weierstrass. I don't know. Sorry. There might be another I or an E somewhere mixed in there. Okay, so let's prove this. So, X is compact, which means it has two things. What two things must it be? Bounded and also closed. Okay, so this is the proof. So because X is bounded, that means that we can draw a ball around it. Okay, that means that there exists a positive radius such that X is a subset of the ball of radius r centered at 0. Okay. So now, suppose that it's like this. That we've got a set X, and it's over here and doing its thing. Okay, so the boundedness says that we can put a ball around it. And we can put a ball around it with this radius. Now I'm going to select either that radius or a larger radius. I want the radius to be, no, it doesn't even matter. We'll select any radius. So that radius. Okay, so we have it in there. Zoonite. Okay, so it's contained in there. Now, what I'm going to do is I'm going to put this ball inside of a slightly larger square. So this is a circle. Remember, this is an Rn, so really this is a ball. This is a sphere. But I'm going to put this inside of a box now. Okay? And so this one is inside of a box. And I'll make the box big enough to where the square and the circle, they don't intersect. Okay? So we've got a set X that's inside a ball that's inside a square. And now I'm going to move the bottom left corner of this square to the origin so that we can consider this to be the new origin. And then I'm going to divide all points by the length of the square. So suppose I do that I take this square, I move its bottom left corner to the origin, and then divide all the points by the length of the square. Then where will we be sitting inside? We'll be sitting inside the unit box. That's where we'll be. We'll be in the unit box. Okay, so without loss of generality, this square is the unit box. That is to say, it is 0 closed at 0 to 1 and then raised to exponent n, which is to say it's this Cartesian product, this Cartesian product, this. So a few pages ago, this was the unit box in R2. So I'm talking about the unit box in Rn, but for sake of argument, I'm going to draw it with 2. Okay. So now, we've got the box, and we've got the set in it. So here's our box. And we've got the set sitting inside of it. So this is set X. But then we have a sequence X. We've got a sequence X. So it's the little green dots that I'm drawing. So it's the little green dots that we're interested in. And there's infinitely many of those green dots. So now what we're going to do is we're going to take this box and we're going to cut it into, we're going to bisect it in all directions. So because of this drawing, there's going to be 4 pieces. And what I want you to observe is that how many pieces are there? There's 4 pieces. Okay. And how many little green dots are there? Infinitely many. And because there's infinitely many green dots, at least one of these pieces has infinitely many green dots in it. Because suppose if that weren't true. What if they all had 10 dots in them? Then where'd all the other dots go? Right? What happened to all my dots? One of these boxes has infinitely many dots in it. One of these has infinitely many xi in it. At least one. They could all have infinitely many in it, for that matter. Yes?
Do those sections have a name? Like, do we call them partitions or something specific?
No. I don't know of a specific name for them. So at least one of these has infinitely many xi in it. Yes?
Sorry. What if the place we make the division has our point that these dots converge? Thus, any epsilon will be equally in one box and the other.
We'll handle it.
Okay.
So at least one of these has infinitely many. So in my drawing, at least, it seems to me like it would be the top left one, right? This one doesn't have any, but that's okay. So whichever one of those boxes has infinitely many, call this box B0 for box 0. And choose an xi that is in that box 0. Choose one of them. And I want you to call it, we will refer to it now as xi0. because that's the first choice that we made. So for example, we don't know where it is in the sequence. We might have just picked, we might have just said that we're going to let xi0 be x 24. Maybe it's the 24th one in the sequence. And we're just going to forget about 1, 2, 3, 4, all the way up to 23. Just forget them. We're just going to forget them, and we're just going to take the 24th one. Okay. So now, this box. That's my attempt to copy that top left corner. So that's box 0, and we selected one of those green points in there. So now we're going to cut this box into pieces. 4 pieces in my picture, but generally more pieces if it's in a higher dimension. What must be true about one of these? One of them has to have infinitely many points. One of them has to have infinitely many points. Has infinitely many xi. And we'll say that the box that we select, because we could select any one of them, we'll say that we are selecting box number 1. We'll call it, whatever we choose, box 1. And we will select xi1 to be some point that's in box 1. So we're calling it xi1 because it might be the case, first we selected point 24, the 24th one in the sequence. So now perhaps we selected, this is just for example, maybe we selected xi1 is x, and what am I going to say? 51. First we selected point 24, then we selected point 51. Okay, so we just have to keep selecting ones that are more than the last one. So the only requirement is that I1 is more than I0. You can't choose any. If you selected 24, you have to next select something more than 24. So we'll continue to do this in the sort of obvious way. We'll continue, and what we'll have is that B0 contains B1, which contains B2, etc., on down the line. So we have these boxes that are all contained in each other. We have xi0 is a point that's in box 0. We have xi1 is a point that's in box 1. We have xi2 is a point which is in box 2. And the indices that we've selected are such that I0 is less than I1 is less than I2, etc. Kind of a complicated construction. Okay, so now, here's the thing. Every time that we made this choice, we put this box as the unit box. That means that every one of these xi that we chose, what is their leading binary digit is 0. So they're all 0 point something. They're all 0 point something. And every time you choose one of these boxes, what choice are you making about the bits? You're making a choice about the bit. So what this is saying is that by the time we've picked box 0, we've picked bit 0. By the time we've picked box 1, we've picked bit 1. And by the time we've picked box 2, we've picked bit 2, all the way down the line. So by the time you picked box K, you've picked bit K. Oh my goodness. So, what we have is something like something like the following. So now I'm going to write something that's in the reals, only because otherwise we have too many indices running around. So what I mean is I'm going to write a one-dimensional thing. So x0 has to look like 0 point some bit. 0 point, actually we're going to call that bit 0. And then these could be anything. x1, what's going to be the first bit of x1? B0. And when we chose x1, we also chose bit 1. And we made a choice for all of those, but those are irrelevant to my argument here. And then x2, that means that we know that it's going to be B0 is the 0th bit, B1 is the first bit, and we also know B2. And those are all like that. So what I want you to see is that these x's, they have this kind of agreement with their bits. Okay, so now I'm going to set point A to be, well, what I mean, I'm still having to do it in the reals to avoid the indexing problem. We're going to say that point A is B1, B2, 0 point B1, B2, sorry? Yes, thank you. Oh, man, someone's really trying to get me. 0 point B0, etc., all the way down the line. Okay, and now what's the conclusion? That the sequence, the subsequence that we just made, xik converges, and it converges to what? It converges to A. And because the set X is closed, what can we conclude? That A is in X, which is exactly what we wanted to show. So we did it. We proved a hard theorem. Question?
So can we just like push this a little bit further and say that if our original set had an infinite number of points it converges to, because we can go back and pick another different A as many times as we want because we can make the squares.
Okay, come ask me. Come ask me.